speaker of the day is Kontorovich from Stony Brook University.
All right, well, thanks very much for the invitation and the opportunity to speak here. As the last speaker, I have the honor of inviting everyone to thank the organizers for a wonderful meeting.
If we're doing that already, can we also thank Susie Van Doren and all the staff for their assistance in organizing this meeting.
And I'll be speaking about conjecture Zarembas. So there's a collaborator of Zaremba's. I lost track of, there he is. So I just heard a lot of stories I'd never heard before, so it's very interesting. Anyway, this problem starts with the simplest pseudorandom sequence ever imagined, which is the one that's already on the board. Let me just change the notation slightly. I'll take my modulus to be called D, my multiplier to be called B for reasons my own mishigas, and so this is called the multiplier. This is called the modulus. This is called the shift. Let me just take, for simplicity, the homogeneous case where the shift is 0, and then you send x to multiples of b and reduce mod d, and sometimes usually you add the shift. That's the linear congruential pseudorandom number generator, the simplest one. And so obviously you only have numbers mod d, and so the period of this is at most d. You'd like the period to be as long as possible. So since I've taken the homogeneous case, in fact, the period is just phi of d. So phi of d is largest if d is, so you want, for this sequence to have a lot of points, you'd like b to be a primitive root mod d. And you'd like d to probably be a prime or a power of 2. Let's take a prime. So that would be one ideal setting of a linear congruential number for pseudorandom number generator. And one of the first questions you might ask about it is, well, how random is it? So what's a measure of its randomness? One such test for randomness is the serial correlation test. And we'll just do it for pairs. They're much better. So by the way, I don't know anything about cryptography, but I don't think you're supposed to use these for cryptography. There's a lot of, but they're very good for example, video game consoles. They're extremely fast and use almost no memory. So they do have some use, just not cryptographic ones. So anyway, one test of how random this is so basically you're looking at powers. You're looking at powers of b over d if you run over the whole sequence and you didn't start with a stupid seed. So serial correlation is how well do I know the next entry given the previous one. So if I look at these points, let me reduce mod 1. So now I have a bunch of points in the unit square, and I'd like to know how well this set of points is distributed. So the discrepancy, everybody here probably knows. So this is a set of points. Let's call each point yn. Mod 1. So these are points in the unit square. And the discrepancy measures how well these numbers are equidistributed. That'll tell you that this is behaving like a nice random sequence, that you can't tell where the next entry is given the previous one. So the discrepancy is just, well, let me define it exactly. So it's the number of these yns that lie in some ball over the total number of yns, so there's d of them, minus the measure of this ball, and you'd like this to be small. Let's say soup over. And there's different discrepancies depending on what kind of balls you allow. Let me just be a little vague about what the discrepancy is. So let me just show you a picture to get us thinking about this. So here's one. I've taken d equals 4547, which you can verify as a prime number. And I've taken b equals 3523, which you can verify as a primitive root mod d. And when you plot these pairs, you get that. So as you might imagine, that is extremely well equidistributed. It looks like a grid. It's has very low discrepancy. So this is the theorem of Zaremba's that got everything started from 1966. And the theorem is, for such a sequence, the discrepancy is at most something complicated. Where's the constant? A, there's an A in there. 4a over log a plus 1 d, log d over d. This is the key point, plus 4a plus 1 over d. So let me just put some quantifiers. So given b and d relatively prime, when you take this sequence, the discrepancy of that sequence is bounded by this parameter for some a, which I'll tell you about in a second, for some constant a. So just to get our bearings, so this is to get our bearings, compare to the, if you just took d random points in the unit square, what would its discrepancy be? So the law of central limit theorem tells you that the average discrepancy is like 1 over root d, or root log d over root d. So here's a random collection of the same number of points, 4,500 points. Yes. Yeah. Yeah. So this is, so now I'm taking rectangles. So the point is there's a lot of clusters and there's a lot of white spaces, so it's a bit less well distributed compared to this set, which is very nicely distributed. And let me just point out something else, which is that this main term is sharp. So this is a theorem of Wilfried Schmidt from 72, that for any d points in the plane, so for any yn in the unit square, the discrepancy is at least log d over d. So this leading term is sharp. The only thing that you can possibly hope to help with is the constant. So let's discuss the constant. What is the constant? Zaremba gives it explicitly. And maybe not surprisingly, it has to do with the continued fraction expansion of b over d. So if we write b over d in its continued fraction expansion, then for some a becomes where a is just the largest entry. And so let me tell you what it is in this case. So if you write 3523 over 4547 in its continued fraction expansion, if I've copied this down correctly, that's it. So a is equal to 3. What's that? That's a 2. This one you're complaining about? This is a 3. Should I? Yeah. So just to show you how this can go wrong, so if I take, now this is 3523, I'm going to change 3523 to 3535, which is still a primitive root. But now the continued fraction expansion's got a really big entry in it. And you still get something grid-like, but obviously this is nowhere near as well distributed as this sequence, even though it has the same number of points. Okay, so it's very sensitive to this parameter a, as evidenced by this main term. Okay, so what's Zaremba's conjecture? So you would like to be able to take a as small as possible and get the best degrees. But you would also like to have the flexibility to choose a sequence of any length you'd like. And that's exactly the conjecture. So the conjecture from 1971, conference in Montreal, appeared in the proceedings in 72 is that, well, let me give you just a little bit of notation. So let Ra be the continued fraction expansions, A1, AK, the finite expansions with the AIs bounded by A. So these are all fractions whose entries are at most A. And let dA be the set of denominators, continuance. So if I write this as a fraction, b over d, then d, the set of d's, is exactly the set of dA. And the conjecture says, for some a sufficiently large, this set of denominators is everybody. So you have complete flexibility in the sequence, in the length of the sequence you'd like to choose. And it even tells you what a is. 5. A equals 5 should be enough. So this conjecture is absolutely, completely elementary. You can explain it to a 9th grader. Let me rephrase it. For every number d, there is some number b relatively prime to it, so that the continued fraction expansion of b over d uses only the entries 1 through 5. That's the problem. Okay? So it's a beautiful elementary problem. So let me just tell you a second why a equals 5. Well, let me show you one other picture, which is related. So here's one thing that this conjecture is related to. Here's the unit tangent bundle on the modular surface, upper half plane mod action of SL2Z. You can't see it too well, but here's a vector. That vector is pointing, its visual limit point is exactly this fraction 3523 over 4547. I've written out its expansion again for you. And if you take the geodesic flow that points to that and you fold it back into the fundamental domain, well, of course, it's a geodesic that's pointing to a rational point. So eventually, it has to escape to the cusp. It's a divergent geodesic. And there it goes, escaping to the cusp straight up to infinity. But before it does so, it can only spend the rest of its life in this fixed region. And the fixed region is exactly being governed by its continued fraction expansion. So if you read off the cutting sequence, if you look at the triangle, well, so there's an easy way to read off the cutting sequence. You have if you cut a triangle, you always cut with 1 point on one side and 2 points on the other side. So you keep track of left, right, left, right, left, left, right. The sequence of changes is exactly, almost exactly. Caroline's series explained how to do this the right way. This isn't the right picture. But we'll basically read off this continued fraction expansion. So not having large entries means you can't go high in the cusp. Of course, at the very end, you have to go all the way into the cusp, but otherwise. So I point this out to relate it to recent work of Kurt McMullen, where he's studying a similar problem where he wants to find not divergent geodesics, but closed geodesics, which spend, so closed geodesics will be defined over some number field, and he wants to fix the number field and show that he can find infinitely many closed geodesics defined over a fixed number field, which live in a compact region. So that's just one relation. Let me go back to this question why a equals 5 is interesting. So for a equals 4 is false. Uh, 54 is not in D4. So whatever numerator, check every number that's relatively prime to 54 and write out its continued fraction expansion. It always uses the digit at least 5. Okay. Excellent question. So I'm getting right to that. Yeah, let's ask, what if you allow finitely many exceptions? I think in the case of D4, there are 3 exceptions known. So then you have the conjecture of Hensley. From 96. Actually, it's kind of interesting. Niederreiter, in a survey in '78, says he believes a equals 3 will contain every sufficiently large number, but believes a equals 2 will have a positive density, but doesn't say it's a positive proportion. But Hensley conjectures that D2 already contains every sufficiently large number. So finitely many exceptions if you allow only the letters 1 and 2. Okay? So let's discuss this conjecture a little bit. So let me introduce a little bit more notation. His conjecture is actually quite a bit stronger than this. So let me introduce this Cantor set, CA. I'll just extend these finite continued fraction expansions out to infinities, A1, A2, out to infinity, with all AJ at most capital A. So this is some Cantor set on the line, on the unit. T is ready. I don't know what that bell means. So you have this Cantor set, 0, 1. Here's the point 1/2. So anything in this region has its first digit equal to 1, up to a third has its first digit equal to 2, and so on. So I cut out up to 1 over a plus 1. Anything bigger than this will not be in your Cantor set. And then you check the second digit. So you cut out that region, that region, that region, and so on. So it's some Cantor set, and it has some Hausdorff dimension. So let delta A be the Hausdorff dimension of this Cantor set. Just to get our bearings straight, what if A equals 1? Well, so the Cantor set, so C1, is just the sequence of all 1s, which is the singleton of 1 over the golden ratio. The only rational numbers, so these will be the partial convergence of things in this. So the only rational numbers you get are quotients of consecutive Fibonacci numbers. And of course, the only denominators you get are the Fibonacci numbers. And the Hausdorff dimension is 0. Already for A equal 2, you have that delta 2 is equal to 0.53. So Jenkinson-Polycott in 2001 computed this to 25 decimal places of accuracy. Okay, so we really know this number. If knowing a number means computing 25 of its decimal places, then we know this number. And let me just tell you what happens asymptotically. So for A large, of course, you're cutting out smaller and smaller segments, so you would expect the dimension to approach 1, and in fact it does. So this is a theorem of Hensley from '89 that says the dimension is equal to 1 minus this nice number, 6 over pi squared a, minus log a over pi to the 4th a squared. I could be making this up, plus 1 over a squared. Anyway, the point is, as a gets larger and larger, you're approaching 1. The dimension of the resulting Cantor set approaches 1. So now let me explain what Hensley's full conjecture is. You don't need to take the entire interval from 1 to a. Just take any alphabet. Let a be some alphabet of allowed partial quotients. Let CA be all the continued fraction expansions, infinite continued fraction expansions, from that alphabet. RA, the fractions, DA, the denominators, the continuants, and delta A, the Hausdorff dimension. Then Hensley's conjecture this one is that the set of continuants will contain every sufficiently large number if and only if this Hausdorff dimension exceeds 1/2. And of course, this number is greater than 1/2. So that's why he's conjecturing that A2, D2 already contains every sufficiently large number. Okay, it's not hard to see the implication this direction. It's basically obvious. We'll see in a second. The opposite direction, obviously, is the whole point of the story. Let me just show you some pictures so that we can get a feel for what's going on. So here's the I took all the numbers d up to 1,000, and I looked at the fractions b over d, which are written using only 1s and 2s. And I plotted the fraction b over d against d. And you can see how sparse this is, which is possibly why Niederreiter was very careful about saying d equals 2, a equals 2 will already contain every sufficiently large number. Let me show you a slightly, take this picture out a little longer. I'll take it out not to 1,000 but to 10,000. It's starting to fill up, but there are still plenty of d's whose fibers are empty. So this problem, of course, at the boundary, in the limit, the only continuants you're getting are continuants that are approaching numbers in the Cantor set. So this boundary, you're seeing exactly this Cantor set that I drew there, just horizontally. And so the question is, you have this large set in the plane. When you project it to the d's, do you get every d, or every sufficiently large d? That's really the problem. And if you take a equals 5, which is Zaremba's original conjecture, well, first of all, the low numbers miraculously all match up. For d equals 4, it looks almost the same, except you're missing the number 54 here. There's no fiber above it. But here's the limiting Cantor set, and you see the projection is full. Okay, so that's the problem. So this really looks plausible from the picture, maybe plausible from the picture of a equals 2. But unfortunately, as stated, it's false. So here's the lemma. Take the alphabet 2, 4, 6, 8. How far did I have to go? 10. Just one more. I just needed enough even numbers so that I could get the dimension to be 0, 5, 1, 7 or something, whatever it is. It's bigger than a half. And for that alphabet, all of the continuants, all the denominators, will be congruent to 0, 1, or 2 mod 4. Okay, so you have to throw in local obstructions. There's more than one completion of the integers. It's not just the Archimedean parameter. You also have to take care of local obstructions. But beyond the local obstructions, it seems possibly plausible that this conjecture is true. Okay, so let me tell you about some partial progress towards the conjecture. So what's known? So first of all, there's a theorem of Niederreiter from 1986. So this is the theorem of Niederreiter. Niederreiter. Close enough. From 86. That the powers of 2, the denominators which are powers of 2, so remember, for the original application, we wanted either primes or powers of 2. Well, it doesn't say anything about the fraction on the numerator, which you want it to be a primitive root mod 2. But anyway, the powers of 2 can be written using only letters 1 through 3. In fact, this works for powers of 3 and probably can be pushed to powers of 5. So if we let dA of n be the number of elements in dA up to n, this tells us that dA of n is at least, well, we've produced log n numbers. Actually, we'd already produced log n numbers because we had the Fibonacci numbers. Okay. Let me tell you a theorem of Hensley's from there's 3 papers, 92 I want to say. Yeah, 92. So you see you have this product structure. So let's look at exactly this product structure. how many fractions do we have, b over d, in Ra, so that d is at most capital N. Let's restrict. How many points are there? How many dots are there on this picture? He proves that up to constant, this is n to the twice delta A. So if you like in the plane, this is a set of dimension 2 delta. And so a trivial consequence of this, there'll be two trivial consequences. One trivial consequence, well, the fiber, there's n to the 2 delta points, and we're interested in having non-zero fibers. But the fiber above any point has at most n entries in it. D is at most n, and above any d, there's at most d entries, which is at most n. So trivially, we have dA of n is at least n to the 2 delta minus 1. That's completely trivial. It's even more trivial because it's really trivial if delta is less than a half. Then it doesn't tell you anything. Slightly less trivial, but I'll also write it as trivial, as you'll see in a second how to prove this, is actually you can get n to the delta just out of this, just out of Hensley's theorem. So I'll explain how to prove this in a minute. I'll put a star to remind myself to tell you later. Okay. So any questions so far? Everything's clear, right? Everything's trivial so far. Well, no, there's some. So let me tell you theorem. I should have said this is all joint. Everything I'm talking about is joint work with Jean Bourgain. Well, I'll just write it here. So this is theorem 0. This is 2011, I guess. Yes.
Sort of looks like the Cantor set.
Yes.
The integral.
Yes.
Which would be n to the 1 plus delta. If it was just completely solid going.
Yeah, but it's not completely solid. There's a lot of gaps. You should look better here. Or better yet, I mean, there's just too many points for you to see how thin this is.
Little tiny gaps on the right.
There's each fiber is also looks very small. The number of elements in each fiber, you'll see in a second. The multiplicities are not. You don't have a full Cantor set at each place. The dots are too thick. This is a better picture to look at. So above each D, you want to know that there's at least one entry, but there are very few. You don't have n to the delta points. Yeah. Yeah. This is extremely crude. This is less crude. Of course, the conjecture is, I should have said, the conjecture from this point of view is that dA of n is n for A equals 5. Or maybe n plus big O of 1 if you're missing constant number of points. Okay, so the first theorem is just a tiny little improvement on the trivial bound. So if we had just 1 minus delta here, that would be positive proportion, of course. So 2 delta minus 1. Delta needs to be bigger than a half for our theorem to have any implication, and over 5 minus delta. So if you look at this asymptotically, as delta approaches 1, you're getting a 1 here and a 4 there. So it's about a quarter times 1 minus delta. It adds, so this applies for any A. In particular, it'll replace this 1 by a 7. It adds something in the third decimal place. Okay, so it's theorem 0. It's just an appendix. So theorem 1, this is all the same work. Positive proportion. For A sufficiently large, I think, what is it? 2189. For A around 2,000, a little more than 2,000, we get a positive proportion. Theorem 2. So this only applies for A large. This theorem applies for any A. This is a small improvement, but it works for even A equals 2. Everything else will need A to be large to kick in. So theorem 2 is that with the same A, d of A is n times 1 plus little o1. So that's density 1. Of course, it's better than theorem 1, but I'll explain why I'm separating these out. Theorem 3 theorem 3 is the size of the error term, not just little o1, but n to not quite a power savings, but better than any power of log savings. So some constant over log n. And moreover, each d that's produced here, so this is your question about multiplicities, each d in this set has multiplicity which is consistent with what you should expect, and not that the size of the set is n to the 1 plus delta, but it has multiplicity n to the 2 delta minus 1 almost. So the set of d's is thick. Almost every d is there. But the multiplicity above each d is not n to the delta. It's n to the 2 delta minus 1. So let me just show you a plot of the multiplicities. So here's for a equals 5. The dimension for a equals 5 is like 0.83. And above each d up to 1,000. So the multiplicities are all non-zero. That's nice. And I plotted the curve x to the 2 delta minus 1. And it fluctuates quite a bit, fluctuates around these. So theorem 3 is significant in being better than those two because it has a corollary to the problem stated here, to the original motivation. So the corollary is that for a equals, I need one more than what's there, 2189, 2190. There are infinitely many primes. Primes, well, I'll call them D. It's perverse to call a prime D. And primitive such that there exists a primitive root B mod D with B over D in RA. Okay, so it produces infinitely many primes and primitive roots mod that prime, having this uniform absolute bound 2190. Okay, so let me just prove this corollary given this theorem. It's kind of a cute argument. Any questions so far? It's the end of a long day, huh? Or this is too easy. So let me prove the corollary. Let's take the primes up to n. I want primes that are congruent to 3 mod 4. And I want the property that if I have a divisor of the prime, not p, but p minus 1, well, 2 is a divisor, so I want a divisor that's bigger than 2, then that divisor is quite large. Let's say n to the 1/10. So a usual sieving argument will tell us that the number of primes in this set is n over log n squared. In fact, Chen's theorem, I can take n to the 1/3 here. OK, well, that means the intersection of this set with our dA from this theorem, the exceptional set is n to the minus constant log log. And the number of points here is n over log squared. And so there's too many points to fit in the exceptional set. So this is infinite. In fact, is bounded below by this. So take D in this intersection, So the theorem also produces a large multiplicity above each d. So that means there exist b1, b1 up to bk, so that bj over d is in Ra. So those fractions, we don't just produce a d, we produce these points above the d. The fiber above the d has k elements, where k is at least, well, n to the 2 delta minus 1. For delta large, this number will be close to 1. So let's say k is at least n to the 10/11. Okay, so we produced a lot of points above 1 point. The fiber above a single point is large. Okay, well, what does it mean that these bk's are primitive roots? We need to force one of them to be a primitive root. So take any primitive root. Root r is a root mod d. And write bj as r to some kj. So now we have a list of kj's, integers k. So then kj is, so bj is a root. Bj is a root if and only if kj is relatively prime to p minus 1. Okay? Well, it doesn't have to be relatively prime to p minus 1. I should have said as I'm erasing this, what we really prove is that as long as the dimension is sufficiently large, you get this behavior. So the dimension being large, getting you this behavior is some analog of this Hensley type conjecture. Okay, we have these points kj, and we want to know that they're going to be relatively prime to p minus 1. Well, so if kj and p minus 1 have a factor greater than 2 in common, then that factor is extremely large. So the number of such kj's, so the number of k which have a larger factor is at most, well, if the divisor is n to the 1/10, there's at most n to the 9/10 such divisors. But the number of k's we have is n to the 10/11. So we can throw these away. So throw these out. Throw these out. It might be the case that one of the kj's is relatively prime to p minus 1. Well, then we're done. But it also might be the case that the greatest common divisor is exactly equal to 2. So if k and p minus 1, well, if k is even, then we're stuck and we can't throw these out. But then look at minus bj, so kj, which is just minus r to the kj. That number is a primitive root because minus 1 is not a square if p is 3 mod 4. So this number is a root. So this number, which I can, so then d minus bj is a root. And d minus bj over d is 1 minus bj over d. And now you need an elementary fact, which is that if p over q is in Ra, then 1 minus p over q is in Ra plus 1. This is trivial. Okay, so to get this corollary, which is our initial motivation, that we want prime moduli and primitive roots mod that prime, we need the quantitative statement here that we have many points and we have a small exceptional set. We'll give the qualitative statement here that we're finding primes and primitive roots mod that prime. Okay. So where is all this coming from? It's coming from the following trivial observation. We're certainly by far not the first to see this. Everybody here probably surely knows it. So here's the trivial observation that b over d has continued fraction expansion a1 up to ak if and only if the matrix 0, 1, 1, a1 times the matrix 0, 1, 1, a2 times the matrices 0, 1, 1, ak when you multiply out these matrices, you get something, something, B, D, which is why I've been calling them B and D all along. Okay, so this is just trivial. This observation is extremely powerful. Let me show you. Well, first let me prove this triviality, trivial 2. So proof of trivial 2. So BD is a matrix of this kind, right? So the number of BD, we have Hensley's theorem. The number of pairs B and D is up to n, intersect the ball of radius n, is n to the 2 delta. Okay, so I claim, so let's take the matrices that are produced. Well, we'll do this in a second anyway. Let gamma A be the semigroup generated by matrices of the form 1, 1, A, with A being at most A. So any word in matrices of this form where the digits A are bounded by capital A is exactly what produces matrices whose last entry, whose second row is the fraction B over D. Well, one trivial thing to notice is if star star BD is in gamma A, then so is its transpose. And that's simply because each of the generators is transpose invariant. So just reverse the order and you get the transpose. And now look at what happens if you multiply this element, which is in the group, by another element in the group. You get, all I care about is this row, which gives me a B plus D. Okay, so there's a sum set type phenomenon happening here. So B plus D is in dA if B over D is in RA. And now this trivial statement really is trivial, because the number of pairs B and D in this ball is the same as the number of pairs B plus D, D. Since you can recover, knowing B plus D, D, you can recover BD and vice versa. I don't care about the constant. Okay, but so I've just changed which line I'm projecting onto. Instead of projecting down on the ground and looking only at the D's, I'm allowed to project onto the D or onto this line B plus D. Well, if each of these sets has size at most x, the size of the product set is at most x squared, which means one of these sets has size at least n to the delta. And each of these sets are in the same set, so this set has size n to the delta. Okay, so that's the triviality. Now, so let me remind you about another theorem that Bourgain and I proved, I guess, a year ago. Which is the following. So let gamma be a subgroup of SL2Z now, and I'm taking a group which is free, has no parabolic elements. These are really geometrically finite. These are harmless assumptions. And the dimension of gamma, which is the Hausdorff dimension of the limit set of gamma. So gamma acts on the upper half plane. There's some limit set on the ground. That limit set has some Hausdorff dimension. And we need this dimension to be very near 1. So if you give me a group like this, then the set D is the set of D elements. So this is gamma times E2 will give me the second row. And if I take the inner product of that with D2, that'll give me the second entry. So this is exactly the set of Ds of the matrices in gamma, which is exactly what the Zaremba problem is asking for, the set of these Ds. So you want to pick off this element. Which Ds are there? This set D almost satisfies the local to global principle. Has an almost local to global phenomena. So what do I mean by that? What I mean is, if we let n be called admissible, if it satisfies the local obstructions, if n is in the set, so now I'm just calling it D, mod Q for all Q. If it doesn't satisfy the local obstruction, there's no way it appears in the set. So n is admissible if it passes all the local obstructions. You just take your set D, you reduce it mod Q for every possible Q, and check that n lies in the set. And let n be exceptional if it's admissible, if it fails the local to global principle. Local to global says if you're in there locally, you're in there, you actually are in there. So if it's admissible, but n is not in the original set. So if it fakes you out mod every Q, but isn't actually there, then we call that set exceptional. So what we really prove is the number of n up to big N, which are exceptional, is at most n to the 1 minus something. Okay, so power savings. So here we're getting a actual power savings. This is only n to the minus. It's not a full power off the exceptional set. Okay, so this is how I knew when I saw Hensley's conjecture that you have to be careful about these local obstructions. You have to check this admissibility. And well, why am I stating here something much weaker than what we have there? It's the same problem, right? It's the same theorem. So why aren't I just applying this result to this problem and getting the answer? The problem is this is a group. Gamma is a group in SL2Z. And what we have here is a semigroup on these generators with dimension very near 1 if we take capital A near 1. And we're looking for the set of Ds. Can that possibly have caused difficulties? Well, let me tell you what goes into this theorem. Yes, it does. It completely changes the problem. So let me tell you what goes into this theorem. So what are the tools that go into this theorem? So first of all, we set this up. Basically, if you have something this weird that you're playing with, the only way we know how to attack something like this, even to get started, is the circle method. It's something. As Peter always likes to say, it's a method and not a theorem, because it often doesn't work, but sometimes can be cooked up to work. So harmonic analysis meaning the circle method, and there's a group structure, which maybe I'll have time to explain, which allows you, this group or semi-group structure both allow you to play with bilinear forms. So we cook up the Vinogradov type methods, Vinogradov, bilinear, in fact multilinear estimates. So estimates on multilinear sums. There's exponential sums here. So when you do these exponential sums, you get some bound on the minor arcs in the circle method, and you need something on the major arcs. So for the major arcs, we need, I guess it's also harmonic analysis, but spectral theory. We need the spectral theory of infinite volume. So these are subgroups of SL2Z, which are infinite index in SL2Z, which is why this delta can be less than 1 in the geometrically finite case. Spectral theory of infinite volume hyperbolic surfaces. So this is work of Patterson, Sullivan, Lax-Phillips. We also need the representation theory. So representation. So we have to control there's continuous spectrum here, which is no longer easily controllable just by Eisenstein series methods. So the representation theory, we need Howmore decay of matrix coefficients to take care of the continuous spectrum. So this is now more, decay of matrix coefficients. And we need this spectral gap, the topic that we've been talking about all along. In this setting, the spectral gap for all Q already follows from Gambert's thesis. So an infinite volume spectral gap, exactly in the case when delta is near 1. He needs it to be bigger than 5/6. And you get a uniform spectral gap. As you replace gamma by a congruent subgroup of gamma, you're changing you have towers over your initial surface. And you need to know that the spectrum there stays away from the bottom. The bottom will be governed by this Patterson-Sullivan base eigenfunction, base eigenvalue. You need to know that as you vary the level, as you go to level Q, the next highest eigenvalue doesn't infringe on the base. Well, what happens if instead of working with a group, you have a semigroup? What is the upper half plane modulo a semigroup? It's only a one-way equivalence relation. It's not an equivalence relation. There's no fundamental domain. So spectral theory is out. Representation theory is out. So all of these tools that we had been using. So by the way, I should have said this is developed in a paper with. This is all work with Bourgain and Sarnak. Developing the tools that we need to make the major arcs estimate go through in this work. And all of this is lost when it's stupid, right? It's just the groups or semi-group. What's the difference? I never really appreciated the difference between these things until we got to, when we realized that none of this technology, which is heavy machinery, and none of it applies the second you take away inverses. Okay, but thankfully there's something to replace it. And that is the thermodynamical formalism. Which I just have a minute to tell you about. So we replace the stuff that's all crossed out, with the with the thermodynamical formalism. Meaning symbolic dynamics. So this is the Ruel zeta function, Ruel transfer operator, counting methods of Lally, and well, ingredients from Dolgopiat and Note. Well, yeah, you use it in your paper, so it goes into. What's that? Yeah. And then the spectral gap exactly in this setting proved by Bourgain, Gambert, and Sarnak. We don't, in our application to the counting statement, we only need Lally and your theorem, really. This theorem is proved for Q square free in this paper. And where's Peter? So Bourgain and Varju extended. You asked why you need Q to be arbitrary. In the sieve, you only need square free cubes. But in the circle method, you need arbitrary Qs. So this extension is actually very important for us. Now, let me point out, why did I separate these theorems? Only theorem 3 requires all of this technology. For theorem 1, we work a bit harder on the first step, the circle method. And we set up a multilinear analysis, this bilinear type sums, but they're on every scale. And everything is minor arcs. There's no major arcs. You don't need any major arcs to prove a positive proportion. So this proof is really quite well, once you do these bilinear, this proof doesn't use any machinery. No big machinery.
No major arcs mean that there's no local obstruction. There could in potential be a local
Yes.
obstruction. Where did you see it that you didn't have major arcs?
It's
Use finitely many primes at the time. Maybe you only make Q go up to a fixed number.
Q is constant.
But arbitrarily low. I mean, if the major arc contribution was 0 because there was a local obstruction, which there isn't, as you pointed out.
Yeah.
There is in some other example.
Yes.
Oh, I see. This is not the theorem 2.
It's just positive density. It's just positive density. Theorem 1 is absolutely trivial. Theorem 2, of course, we have to, if there's a local obstruction, there's no way we're getting 100%.
I thought you said all but theorem 3.
So this still doesn't use, so, okay, so this is no big machinery in all minor arcs. For theorem 2, we have to introduce major arcs, of course. So this uses major arcs. But we just need any major arcs at all.
Q gets arbitrarily lowered with fixed. The denominator.
No, we need Q going to infinity, but arbitrarily slowly with n, because we have the minor arcs. So to get Q going arbitrarily slowly, we actually change the analysis from analysis on the circle, major minor arcs on the circle, to flipping back to analysis on the integers. So you need to know just a little bit of equidistribution mod Q and a little bit of Archimedean equidistribution, which you can cook up bare hands again. So this theorem is again without using the heavy machinery. Of course, once you want to know something this precise, now we're applying all of these methods.
So we don't use Lally instead of Theorem 2?
We do use Lally. We use Lally even in theorem 1. But that's sort of, yeah, but I mean, Hensley can also be proved by Lally, so I'm sort of, yeah, you're right. We use Lally in theorem 1. But by big machinery, I guess I mean a spectral gap, this thermodynamical formalism with the gap built in. So without the gap, we just use Lally. Okay, so let me just say one other thing, which is that the whole reason this is working is that there are no local obstructions. I meant to say this looks like an infinite number of Q's you have to check for D to be admissible. Admissibility seems like a condition you have to check for infinitely many Q's. But there's the strong approximation which is at work here, which tells you this question can be settled after finitely many Q's, which you can figure out just given the generators of the group. So that's exactly what was wrong in Hensley's original conjecture, that strong approximation fails at the prime 2, which is why D's were not well distributed mod 4. But for any A greater than 2, in the original Zaremba problem, everything is on 2. So that's why there's no local obstructions here. OK, let me stop there. Thanks for